Imagine you are in a cozy coffee shop. The date is September 18th, 2025. The aroma of roasted beans fills the air. You connect to the free Wi-Fi named coffeehouse_guest without a second thought. It seems convenient, a modern-day necessity for remote work or casual browsing. You check your bank account, reply to a sensitive work email, and maybe scroll through your private messages. In this moment of digital connection, you feel productive and secure. But this feeling is often an illusion. The very openness that makes public Wi-Fi so appealing is also its greatest weakness. You are broadcasting your digital life into a shared space and you have no idea who else might be listening. This shared space is not like a private conversation in a quiet room. It is more like shouting your secrets in a crowded public square. Every piece of data, every password, every message, every website you visit, travels through the air as radio waves. Without strong encryption, this data is an open book. An attacker sitting just a few tables away can easily intercept these signals. They don't need sophisticated government-grade equipment. A simple laptop with freely available software is often enough. They can capture your login credentials, read your emails, and steal your personal information, all while you sip your latte, completely unaware of the digital eavesdropping happening right under your nose. The danger goes beyond simple eavesdropping. An attacker can set up their own Wi-Fi network with a convincing name like coffeehouse_free_Wi-Fi. This is known as an evil twin attack. Your phone or laptop, programmed to connect to familiar networks automatically, might connect to this malicious hotspot without you even noticing. Once you are connected, the attacker controls the entire flow of your internet traffic. They become the gatekeeper to your digital world. They can redirect you to fake banking websites to steal your credentials or inject malware directly into the websites you visit. This is a profound violation of your digital security, and it happens because we implicitly trust networks that offer us convenience. The fundamental problem is one of trust and verification. We trust the network name displayed on our screen. We trust that the connection is secure. We trust that the other people in the coffee shop are just like us, simply there for the coffee and the internet. But in the digital world, trust without verification is a recipe for disaster. The wireless signals that carry our data are invisible, and so are the threats that exploit them. We have built a world of incredible connectivity, but we have largely forgotten to build the necessary layers of security to protect ourselves within it. Our digital lives are more exposed than ever, and the places we feel most comfortable are often the most dangerous. The threats that plague wireless networks are diverse and cunning. They go far beyond the simple evil twin attack. One of the most common is the man-in-the-middle or MITM attack. In this scenario, an attacker secretly positions themselves between you and the network you are trying to connect to. They intercept all your communications, relaying them back and forth, making it seem like you have a direct connection. To you, everything appears normal, but the attacker can read, modify, or inject any data they wish. They can steal your credit card details when you make an online purchase or alter a bank transfer amount. It's the digital equivalent of a postal worker opening your mail, reading it, and then sealing it back up before delivering it. Another insidious threat comes from botnets. A botnet is a network of compromised devices, often including routers, smart TVs, and even security cameras, all controlled by a single attacker. These infected devices can be used to launch massive attacks. For example, a botnet can be instructed to flood a company's wireless network with so much junk traffic that it becomes completely unusable. This is called a distributed denial of service or DDoS attack. Your own router, sitting quietly in your living room, could be part of an army of devices used to take down a hospital's network or a financial institution's online services, all without your knowledge. The individual devices are not the target, they are the weapon. We also face threats like packet sniffing and session hijacking. Packet sniffing is the act of capturing and analyzing the data packets that travel over a network. If the data is not encrypted, the sniffer can reconstruct everything from emails to passwords. It's sort of like wiretapping a phone line. Session hijacking takes this a step further. After you have logged into a secure website, your browser maintains a session with the server. An attacker can steal the digital token that identifies this session and use it to impersonate you. They don't need your password, they can simply take over your active login, gaining full access to your account. These threats are fundamentally different from those on wired networks. On a wired network, an attacker typically needs physical access to a cable or a port. Wireless networks, by their very nature, broadcast their signals everywhere. The boundaries are not physical walls but the effective range of a radio signal. This makes them inherently more accessible to attackers. The battlefield is not a server room, it is the air itself. Defending against these invisible, ever-present threats requires a different way of thinking and a new generation of tools designed for the unique challenges of the wireless world. The old rules of security no longer apply when the network has no clear perimeter. For decades, we have relied on traditional security tools to protect our networks. Firewalls, intrusion detection systems, and antivirus software have been the cornerstones of cybersecurity. These tools operate on a set of predefined rules. A firewall, for example, might be configured to block traffic from known malicious IP addresses. An intrusion detection system might look for specific patterns or signatures that match known types of attacks. This approach worked reasonably well in a world of static, predictable threats. If you knew what an attack looked like, you could write a rule to stop it. This is signature-based detection. The problem is that today's wireless threats are no longer static or predictable. Attackers are constantly innovating, creating new forms of malware and devising novel attack techniques. A new variant of a virus can be created in minutes, rendering signature-based antivirus software obsolete until it is updated. An attacker can use constantly changing IP addresses to bypass a firewall's block list. Traditional tools are always one step behind. They are reactive, not proactive. They can only defend against threats that have already been seen, identified, and cataloged. They are fighting yesterday's war, while the enemy is already planning tomorrow's attack. Consider a zero-day attack. This is an attack that exploits a previously unknown vulnerability in software or hardware. By definition, there is no signature for a zero-day attack. A traditional intrusion detection system would be completely blind to it. The attack would succeed, and the damage would be done, long before security experts could analyze it and create a signature to prevent it from happening again. In the fast-paced environment of wireless networks where new devices connect and disconnect constantly, the window of opportunity for such an attack is huge. Relying solely on rule-based systems is like building a fortress with a gatekeeper who only has a list of known criminals. Any new face, no matter how suspicious, is allowed to enter. This is where artificial intelligence becomes essential. AI does not depend on a predefined list of bad things. Instead, it learns what normal looks like. It builds a baseline understanding of a network's typical behavior. It knows how much data usually flows, which devices typically connect, and what kinds of protocols they use. When something deviates from this established norm, even if it is a threat that has never been seen before, the AI can flag it as a potential anomaly. It's not looking for a specific signature, it's looking for suspicious behavior. This ability to detect the unknown is what makes AI a game changer for wireless security. It allows us to move from a reactive to a proactive defense. An AI-powered security system acts as a vigilant sentinel, observing the wireless environment with a level of detail that is impossible for humans or traditional tools. It doesn't just look at the content of data packets, it analyzes the metadata, the context in which that data is moving. This includes monitoring things like packet timing and inter-packet delays. For example, the rhythm and flow of data from a human typing an email are very different from the rapid, automated bursts of data sent by a malware-infected machine communicating with its command and control server. The AI learns these rhythms and can spot the subtle irregularities that signal a hidden threat. The AI also pays close attention to radio frequency characteristics. Every wireless device has a unique physical layer fingerprint, determined by minute imperfections in its hardware. This fingerprint affects the signal strength, phase, and frequency of the radio waves it emits. An AI can learn to identify the specific RF fingerprint of your laptop's Wi-Fi card. If an attacker later tries to impersonate your device in an evil twin attack, the AI can detect that the RF fingerprint of the imposter device does not match the fingerprint of your legitimate device, even if it has cloned your device's MAC address. This provides a powerful layer of defense that operates at the physical level of the network. Furthermore, the AI Sentinel monitors device behavior and communication patterns over time. It learns which devices are supposed to be on the network and what they are supposed to be doing. For instance, it knows that the smart thermostat should only communicate with a specific server from its manufacturer and only send a small amount of data every few minutes. If that thermostat suddenly starts trying to access a file server within the network, or begins transmitting large amounts of data to an unknown address in Eastern Europe, the AI will immediately recognize this as abnormal and highly suspicious behavior. This contextual awareness is crucial for detecting compromised Internet of Things devices. This continuous, multi-layered monitoring provides a dynamic and holistic view of the network's health. The AI is not just checking a list of rules at the network's edge, it is observing everything, all the time, from the physical radio waves to the application layer data flows. It builds a rich, evolving model of what constitutes normal, safe operation. This allows it to detect not just the loud, obvious attacks, but also the slow, subtle ones that are designed to fly under the radar of traditional security systems. It's a new paradigm of watching, one that is perfectly suited to the fluid and invisible nature of wireless environments. For an AI to perform its role as a security sentinel, it first needs data, a lot of data. This data is collected from the wireless network itself, captured from access points, routers, and specialized sensors. This raw data is a torrent of information. Countless packets, signal strength readings, device connection logs, and protocol handshakes. In its initial form, it is mostly noise. It is a chaotic stream of ones and zeros that is meaningless to a machine learning algorithm. The challenge lies in transforming this raw, unstructured noise into structured, meaningful information that the AI can actually learn from. This process is known as feature engineering. The first step is data collection, which, honestly, presents its own challenges. Capturing wireless traffic requires careful placement of sensors to ensure complete coverage without creating interference. More importantly, this data collection raises significant privacy concerns. The captured packets may contain sensitive personal information, from private messages to financial details. Therefore, data must be handled with extreme care. Techniques like data anonymization and encryption are essential to protect user privacy. In many cases, the content of the packets is discarded entirely, and the AI focuses only on the metadata, the who, when, and where of the communication, not the what. Once the data is collected, the process of feature engineering begins. This is where the art and science of AI really meet. A feature is a specific, measurable property of the data. For wireless security, features might include the average size of data packets from a specific device, the time interval between connection requests, the signal-to-noise ratio of the connection, or even the number of different protocols used by a device in a given time frame. The goal is to select and create features that are highly indicative of the behavior you want to model. A good set of features will make the difference between a normal connection and a malicious one stand out clearly to the algorithm. The success of any machine learning system depends almost entirely on the quality of its features. If you feed the AI poor quality, irrelevant features, you will get poor quality, irrelevant results. This is the garbage in, garbage out principle. Creating effective features requires deep domain expertise in both wireless networking and cybersecurity. You need to understand how different attacks actually manifest themselves in the network data. The process is iterative. You propose a set of features, train a model, test its performance, and then refine the features based on the results. It is a meticulous process of turning raw data into actionable knowledge, transforming a sea of noise into the clear signals of a potential threat. After transforming raw data into high-quality features, the next step is to choose the right machine learning algorithms to analyze that data. The choice of algorithm really depends on the specific problem you're trying to solve. For wireless security, a variety of techniques are employed, often in combination. One of the most common approaches is classification. In this supervised learning method, the algorithm is trained on a data set that has been labeled. Each data point in the training set is tagged as either normal or malicious. For example, data from a known botnet attack would be labeled malicious. The classification algorithm, such as a support vector machine or a random forest, learns the patterns and characteristics that distinguish the malicious data from the normal data. An SVM works by finding the optimal boundary or hyperplane that best separates the different classes of data points in a high-dimensional space. A random forest operates by building a multitude of decision trees during training and then outputting the class that is the mode of the classes of the individual trees. Once trained, the model can then classify new unseen network activity in real time, raising an alert if it identifies traffic that fits the malicious profile it has learned. Another powerful technique is clustering. This is an unsupervised learning method, meaning it does not require a labeled dataset. Instead, a clustering algorithm like k-means is given a set of data and asked to find natural groupings or clusters within it. In the context of wireless security, the algorithm might group all the network devices based on their communication behavior. Ideally, all the normal IoT devices would fall into one cluster, all the user laptops into another, and so on. If a device suddenly starts behaving differently, it will drift out of its usual cluster, and this movement can be flagged as an anomaly. This is useful for detecting compromised devices that have started to act strangely. Ultimately, a robust AI security system will use a hybrid approach, combining multiple machine learning methods. Supervised classification is excellent for detecting known types of attacks with high accuracy, but it cannot detect new zero-day threats. Unsupervised clustering excels at finding novel anomalies and behavioral changes, but it can sometimes generate more false alarms. By using them together, you get the best of both worlds. The system can confidently identify well-understood attacks while also maintaining a vigilant watch for anything new and unusual. This layered algorithmic defense is far more adaptable and resilient than any single static security rule. While traditional machine learning models are powerful, they often rely on handcrafted features. This means a human expert must decide which data characteristics are important. Deep learning, a subfield of AI, takes this a step further. Deep neural networks can automatically learn the relevant features directly from the raw or semi-processed data. They're particularly good at finding complex, hierarchical patterns in large datasets. For wireless security, this is incredibly valuable. A deep learning model, such as a recurrent neural network, can analyze sequences of network packets over time, learning the subtle temporal patterns that might indicate a sophisticated low and slow attack that would be invisible to other methods. Deep learning models can uncover relationships in the data that a human analyst might never think to look for. They can process vast and diverse inputs simultaneously, from RF signal data to packet metadata to application layer logs, and learn how these different data streams correlate with each other. This allows for the detection of highly complex attack scenarios that involve multiple stages and cross-layer coordination. The ability of deep neural networks to perform this automatic feature extraction and pattern recognition makes them a powerful tool for building the next generation of intelligent autonomous security systems that can adapt to an ever-evolving threat landscape. However, as AI models become more powerful, they also become more data hungry. This brings us back to the critical issue of privacy. How can we train these sophisticated models without centralizing vast amounts of potentially sensitive user data? The answer may lie in a new approach called federated learning. Instead of sending all the raw data from individual devices or local networks to a central server for training, federated learning reverses the process. The central AI model is sent out to the edge devices, to your smartphone, your laptop, or your local network's router. The model is then trained locally on the data where it resides. With federated learning, your personal data never leaves your device or your network. Only the learned updates to the model, the mathematical adjustments and insights, not the raw data itself, are sent back to the central server. These updates are then aggregated from many different users to improve the shared global model. This allows the AI to learn from a massive and diverse range of data without compromising individual privacy. It is a collaborative approach to building intelligence. It allows us to build smarter, more effective security systems for everyone without forcing anyone to sacrifice their right to privacy. This privacy-preserving approach will be essential for the widespread adoption of AI in wireless security. One of the greatest challenges in deploying any AI-based security system is managing false alarms, or false positives. An AI that is too sensitive will flag benign activities as malicious, overwhelming security analysts with a constant stream of alerts. This alert fatigue is a serious problem. If analysts are constantly chasing down false alarms, they're more likely to miss a real critical threat when it finally appears. The story of the boy who cried wolf is a timeless lesson in security operations. Therefore, a crucial part of building an effective AI system is not just its ability to detect threats, but also its ability to avoid misidentifying normal behavior. Strategies to reduce false positives involve a continuous feedback loop between the AI and a human analyst. When the AI flags an event as an anomaly, a human expert investigates it. If the event turns out to be benign, for example, a new software update that causes a device to communicate in an unusual but legitimate way, the analyst provides this feedback to the AI. The system then learns from this correction and adjusts its understanding of normal behavior. This process, sometimes called human-in-the-loop learning, helps to fine-tune the model over time, making it more accurate and reducing the number of false alarms. It is a partnership where the AI provides speed and scale, and the human provides context and judgment. Beyond just detection, the real value of an AI system lies in its ability to enable real-time response. In the world of wireless security, attacks can happen in milliseconds. There is simply no time for a human to manually intervene in every case. An advanced AI system can be integrated with other security tools to automate the response process. For example, if the AI detects with high confidence that a device on the network has been compromised and is attempting to spread malware, it can automatically issue a command to the network switch or wireless access point to quarantine that device, cutting off its network access and preventing the threat from spreading. This integration creates a comprehensive and automated defense ecosystem. The AI acts as the central nervous system, detecting threats and coordinating the response. It can send alerts to a security information and event management system, trigger a firewall rule update, or initiate a deeper forensic analysis on a specific device. This seamless integration is key to achieving the speed and scale necessary to defend against modern automated attacks. The goal is to build a self-defending network, one that can not only see an attack coming, but can also react intelligently and autonomously to neutralize it before it can cause significant damage. The future of wireless security is inextricably linked with the advancement of artificial intelligence. As our world becomes more connected, with billions of IoT devices coming online, and our reliance on wireless communication growing deeper, our attack surface will continue to expand. The threats we face will become more sophisticated, more automated, and more pervasive. In this future, human-only security teams will be overwhelmed. We have no choice but to augment our human expertise with the speed, scale, and learning capabilities of AI. The trends point towards more autonomous, predictive, and privacy-aware security systems. We will see AI move from simply detecting threats to predicting them. By analyzing subtle precursors and global threat intelligence, future AI systems may be able to anticipate an attack before it is even launched against a specific network, allowing for preemptive defensive measures. We will also see the rise of MLOps, or machine learning operations, a discipline focused on the lifecycle management of security AI models. Just like any critical software, these models need to be continuously monitored, updated, and retrained to ensure they remain effective against new threats and do not degrade in performance over time. Key performance indicators, such as the model's true positive rate and false positive rate, will be tracked relentlessly. Of course, this journey is not without its ethical considerations. The same AI that can monitor a network for malicious actors can also be used for pervasive surveillance. We must build these systems with privacy at their core, embracing techniques like federated learning and a strong commitment to data minimization. The goal is to secure our digital spaces without turning them into digital prisons. This requires a robust public conversation and strong regulatory frameworks that balance the needs of security with the fundamental right to privacy. We are not just building technology, we are shaping the society of the future. The path forward is one of proactive engagement. We cannot afford to be passive consumers of technology. We must become active participants in our own security. This means demanding transparency from the companies that build these AI systems. It means advocating for privacy-preserving designs, and it means recognizing that security is not a product you can buy, but a process you must continually engage in. AI is a powerful ally in this process, but it is not a silver bullet. It is a tool, and like any tool, its effectiveness depends on the skill and wisdom of the people who wield it. The secure wireless future we all desire is not guaranteed, but with a thoughtful and vigilant approach, it is within our reach.